along with limits, we have limits in their properties. These are is direct substitution as shown in the video. And I just want to show you some quick examples here. If you want to take the limit as x approaches 200 of 5, it's 5 because there's no x to substitute in. Here's one where the limit, this is one like you saw in the video, limit is of 3x plus 2 as x approaches 1. You substitute 1 in, you get 5. And here we got some power action going on here. So we can substitute for the power, and we can, or for the base, I should say, and say the limit as x of x squared as x approaches 3 is 3 squared, which is 9. In this next slide, you will find all the properties of limits. This means belongs to the real numbers. That means belongs is a real number, is an integer. J is integers, don't ask me. That's what they made up. And here's all the stuff that goes along with limits as far as all their rules. Usually we use them. All right, these are done to prove what we need to do. We use them, so I don't think memorizing these are important, but just using them, and you'll probably do it inherently anyway. Don't forget that trig functions are peoples too, so we can do limits on those trig functions as seen in that video. Indeterminate forms are 0 over 0, and that's when we use the factor or the rationalizing numerator method. So here's one that you can play with. You can try to factor the numerator, to factoring the numerator into the sums of cubes, if you remember that, and you can play around with that one. The last thing in this section is the squeeze theorem, and it means if we have a function that's in between two other functions, for all, this means for all x in open interval, if both of the limits that are between that function go to some limit, then that function has to go to a limit. And here's a visual example. If I have g going to the limit of wherever c is, that limit, h is the same at c, but f is in between them, then f's going to go to c. Yes, it works, folks. Here is two special trig limits. Okay, the squeeze theorem is used to prove this, but here's two that you need to know. Here is the proof of this underneath, and it just says if we're trying to find out the limit as x goes to 0 of theta, it's 0 here. Limit as x goes to 0 here of cosine is 1. Okay, so I'm sorry, the limit as x goes to 0 here is just 1. Let me erase that here. This is a little confusing. Alright, my bad. It happens. So if we're looking to find out what the sine of x over x is the limit as x approaches 0, like in both of them, well, it's going to be 1, because it's squeezed in between. We know the highest that the cosine can be is 1. That's why I chose the limit there. That's why 1 was chosen here, because the cosine can't get higher than 1. So that's why we have it there. There's the squeeze theorem used. And there's that special limit proved by the squeeze theorem. The limit as x approaches 0 of sine x over x equals 1.